Victoria, from 4.1, 4.1 number 35, sure. Oops. I'm sorry, you're gonna have to like give me just a second while I get this thing in here. Okay, and you said when will the domain not be a real number? Yeah. So you're talking about one of these critical values? Okay. So if I look at 35, first thing I'd want is to identify any places where the function here, g of y, is not defined. So since g of y is a rational function, the only place where I'd have to worry about is when the denominator is equal to 0. So to solve that, I would just be using the quadratic formula since that's not something that's going to factor. And I can see right quick here that I'm going to have a negative number under the square root. Can you see that? I'm going to have 1 minus 4 down there, so that's going to give me a negative 3. So this is basically the domain for this is all real numbers. Okay, so the problem asks us to find the critical numbers. Now I need the domain for g because one of the possible critical values is going to be the place where the derivative is undefined, but it doesn't count as undefined if the function was also undefined there, so I need to make sure I at least like take a look at the the function to start with. Okay, so now we're ready to do g prime of y. Best way to do that is the quotient rule, right? So that's going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So let's simplify this thing down now. Y squared minus y plus 1 minus 2y squared plus 2y plus y minus 1. So when I combine my like terms there, I get negative y squared plus 2y all over that stuff. It's all looking okay so far. We're following along. I haven't made any boo-boos yet. Okay. So that's my derivative. Now the critical values are going to be the places where that derivative is equal to 0 or it does not exist. So the does not exist side is easy for me. I know there's not going to be anything here. And the reason I know that is because, well, if I set the denominator equal to 0, it's the same problem that we had for the parent, or for the original function for g of y, which domain was all real numbers. The denominator was never going to be 0, so we're good there. So to find the place where the derivative is 0. A fraction is equal to 0 when its numerator is equal to 0. So I'll just set the numerator equal to 0 and factor. So I get 0 and 2 as my critical values. Sure. Grab this while I'm at it. I worried about this, the domain in the beginning, because I needed it for this piece, right? Because if the function was undefined at 7, then if the derivative doesn't exist at 7, that's okay, because it shouldn't exist at 7. It's not actually a critical value because that's not part of the domain of the function. The critical values must be in the domain of the function. So that's all I did. That's the only reason I took a moment to check that, was to make sure I didn't end up getting a critical value at the end that's actually not a critical, or get some value where the derivative doesn't exist that's not actually a critical value because it's not in the domain of the function. Is that okay? Good question, Mia? Well, if I have a negative number in the square root, that means I'd be square rooting a negative, which means that the answer is going to be imaginary. So the only places where this y could be, or that denominator could be 0 is if the y is an imaginary number. So the domain then is everything, right? All the reals are going to work because the only thing that can make it 0 is an imaginary. So that's why I stopped when I saw that. I didn't bother to finish it because it's like I got everything I needed. I don't actually care what the number is if it's imaginary. That's enough.
What if it wasn't imaginary? But like the derivative of y does not exist with that number?
So say hypothetically the answer to this was like 3 and -1 or something. So the domain would be all real numbers except for 3 and -1. And when I go down here, this piece would have given me the answers of 3 and -1. But those are not actually critical values because they're not in the domain. Right? A critical value is a place where the derivative is undefined or equal to 0, but the things that are but those values have to be part of the domain of the function. Right? Like if they're not in the domain of the function, then they're not critical values. They don't have to count. Like they're values of g of x, they're values of y, such that they're in the domain of g of y, and the derivative is equal to 0 or undefined. Is that okay? So that's the little hiccup there. Most of the time, I can figure out the domain just by looking at the thing. I don't actually have to do any computation. If this was factorable, that would have been easier, but it wasn't. So, but it was fine. It was easy. It was easy to deal with since the solution was imaginary. But we do need to be like a little bit careful about that, but not super, super duper careful. But it comes up here and there. Other questions? Did you guys look at 4.1 and 4.2 yet? That's okay. I mean, just be honest with me, so I'm not just sitting here like,
I did not look at more
Yeah.
to
Yeah, I've been
4-1.
studying for the test.
So,
okay,
I did actually study for this, so
that's good. Yeah, I mean, I appreciate that. If you haven't done this yet, then like maybe we just not worry about questions right now if we just haven't gotten that far. So I think what I'll do then today is we'll circle back and do 4.3 at a different date because it's kind of based on a little bit on what you did in 4.1 and 4.2. So if we haven't really looked at those things yet, let's not try to build on those things, right? 4.4 is a bit of a standalone, so let's just do that today, okay? 4.4 doesn't depend on anything else that would have happened in 4.1 and 4.2. So let's do that today, right? Rather than do something else. I'm perfectly prepared to do that, and if you guys don't have a lot of questions right now, that's okay. Over break, we can try to get caught back up on things, and I trust you guys to do that.
Yeah, we really do. I think I need.
what is the hospital?
So it's pronounced L'Hôpital.
What?
Yep.
There's no A, there's no I's.
There's an S at the end, and if you carry it over, that's like the.
It's like the power property.
I mean, it's. Oh, I did misspell it. There is. Oops. Control Z.
So, what's up?
Sorry.
See, there is an S.
Yeah.
Power rule does work.
All right. So what we're going to talk about here in section 4.4 is called L'Hôpital's rule. And this is a way to deal with indeterminate form limits. So you remember way back in chapter 2, we ran into rather frequently these limits that took the form of like 0 over 0, or infinity over infinity, or 0 times infinity, or infinity minus infinity, or 0 to the 0, 1 to the infinity, or infinity to the 0. All of these things are what we call indeterminate forms. That means that the answer is not definite. It's not like one thing. It could be lots of things, depending on how you interpret it. So those are limits. We don't say the limit doesn't exist there. We don't say the limit's equal to 0 or infinity or anything else. We can't actually answer the question if we are stuck in one of these indeterminate forms. So way back in chapter 2, we developed some tricks to work around this. So for example, if we look at this limit here, the limit as x approaches infinity of x squared minus 1 over 2x squared plus 1. If we try to do direct substitution, what do we get? We get infinity over infinity, right? That's one of those indeterminate forms. So way back in chapter 2, what we talked about is, well, what you can do is we can multiply the numerator and denominator by like 1 over x squared. When we do that, that becomes 1 minus 1 over x squared over 2 plus 1 over x squared. And now when we do the direct substitution, what do I get when 1 over x squared goes to infinity? 0, right? And same thing with 1 over x squared. So we'd say the limit here is 1/2. You guys remember doing that? Way back in chapter 2. Now that works great if you have like a rational expression like we do here, where it's a polynomial divided by another polynomial. What if it's something that's mixed, like the natural log of x divided by x minus 1? If I plug in infinity, I still get infinity over infinity. That's indeterminate. But I can't use that same trick from chapter 2 on this because natural log of x isn't a polynomial. we're kind of stuck, right? So what we'll use is what's called L'Hopital's rule. So it says that suppose f and g are differentiable and that g prime of x is not equal to 0 on an open interval I that contains a except possibly at a. Suppose that the limit as x approaches a of f of x is equal to 0 and the limit of g of x as x approaches a is 0, or that the limit as x approaches a of f of x is equal to an infinity and the limit as x approaches a of g of x is equal to an infinity. In other words, you have the indeterminate form of 0 over 0 or infinity over infinity. Then the limit as x approaches a of f of x divided by g of x equal to the limit as x approaches a of the derivative of f of x over the derivative of g of x. So, looking at this previous example we just looked at, this is an excellent candidate for L'Hopital's rule. So usually the convention is like, I'm just going to put like an H over the equal sign to indicate that I'm doing L'Hopital's rule here. But Mackenzie?
What this saying is find the derivative at the top and the bottom,
And then we can take the limit.
we take the limit of it.
Yeah, so it's just giving us another tool to use, right? So we do L'Hopital's rule. What's the derivative of the natural log of x? 1 over x. And what's the derivative of x minus 1? 1. So what's the limit as x approaches 1 over x divided by 1? That's just 0. Look at how easy that was. Was that lovely? What a beautiful rule, and so easy to use. Let's do another one. So here we have the limit as x approaches infinity of e to the x divided by x squared. First thing you have to check is it one of the indeterminate forms? So if I do a direct substitution, what do I have here? It's infinity over infinity, right? E to the infinity is just infinity. Infinity squared is infinity. We have infinity over infinity, right? So we'll do L'Hopital's rule.
Okay, but I have a question.
Sure.
And like the one above, like when we substitute infinity for like x squared, we get 0. Like 1 over x squared.
Right.
So why in this one if we do it? If we put infinity to x squared, we just get infinity.
Okay. So just this is a little aside. So the way we think about this is that, right? If we try to do the same thing down here, we would get I have that, right? This is okay. That's not one of our indeterminate forms. This is an indeterminate form. That's kind of the difference of what's going on, Victoria. Is that?
Yeah, it's you still did the x squared limit of infinity, but this time it's infinity squared.
Yeah, I mean, it's fine. I mean,
Oh, okay.
it's the fact that I have the constant on top is the difference,
Okay.
right? Is that, we're okay?
Yeah.
Okay. All right. So back to this example. I'm just gonna, just leave that, it's fine. So the derivative of e to the x is e to the x. The derivative of x squared is 2x. If I do direct substitution again, what am I going to get? Infinity over infinity. Guess what I do? L'Hopital again. Yeah, that's exactly right. So the derivative of e to the x is e to the x. The derivative of 2x is 2. And when I do direct substitution this time, I get infinity over 2, which is just infinity. And that's okay. Isn't this lovely? Aren't you like, why didn't we do this back in chapter 2? The answer is because we couldn't do a derivative back in chapter 2. Like it took like a whole sheet of paper to do the difference quotient, use the definition. Yeah. You can do L'Hopital's rule as many times as you want. You can keep doing it until you get something you can evaluate direct substitution. Isn't this lovely?
I want to keep doing the L'Hopital as well. Eventually get the show equals whatever.
Okay, let's do another one.
Wait, can you only do the cumulative of limit?
Yeah.
Correct. Yes, this is a tool for evaluating a limit. And it just has to be something that's of the indeterminate form. So when we do the direct substitution, if you get 0 over 0 or infinity over infinity, then those are candidates to do L'Hopital's rule. We'll look at how we can do some tricky rearranging to take things that are also indeterminate form but not 0 over 0, infinity over infinity, and shuffle them around so we can do a L'Hopital rule to it. It's quite clever and very exciting. We'll get to some examples here in a few minutes. First thing we got to check here. Make sure it's in the indeterminate form. So if I do direct substitution, I get infinity over infinity, right? So that's good. Okay. Well, L'Hopital's rule, derivative of the natural log is? The derivative of the cube root of x is? Very good. Now, what I would do here Oops. Mr. Kulik, you're being naughty. Hold on a second. What am I being naughty about?
You didn't write your limit.
Well, here's the thing, guys. I caught myself, which is something still, right? You didn't catch me. I caught me. All right. So if I simplify the x's there, I'm just using some algebra. How do I do that? So the 1/3 in the denominator becomes a 3, right? And then I have x to the -1 minus a -2/3. Everybody agree with that? That's just the exponent rules, right? Yes. Yeah. For sure, Mackenzie. So that's going to give me 3x to the -1/3. Or 3 over x to the 1/3. So dividing by 1/3 is the same as multiplying by 3. Well, the 1/3's in the denominator, right? So it's being divided. Dividing by 1/3 is the same as multiplying by 3, right? Or you could think about just multiplying the reciprocal, right? But once I've done this, here's the point. I've done some algebra to rearrange things. What's that limit?
Oh, it's 3 over.
3 over infinity, which is
Okay.
0. Yeah. Right? 3 over huge is
Right.
0. Is this okay?
Yeah, so you just have to keep going, like keep simplifying.
I didn't do any L'Hopital after the first step. All I did after the first step was simplify to see, like, if I plug in the infinities, it's like, well, it's kind of weird what's going on here.
So you just keep simplifying it until it makes sense.
Yeah, I just simplified it till I got to, like, okay, both those x's can combine together. Let's just combine the x's. There you go.
Okay.
And see what I got, right? All right.
Yeah. Okay, now
Like, I
it's
like-
not
oh.
zero.
And this side.
And this.
Okay, first thing we have to do.
I say we separate them.
Nope. First thing we have to do,
Figure out this indeterminate.
check if it's in the indeterminate form, because we can't use L'Hopital's rule if it's not in the indeterminate form. So if I do a direct substitution, what's tan of 0? Okay, on the unit circle, what is tangent? Y over x. Okay. At 0 degrees, what is the point on the unit circle at 0 degrees? 1, 0, right? Everybody agree? So if it's y over x, what is tan of 0? There you go. Everybody happy so far? So what is this? Is this indeterminate? Yes, because it's 0 over 0. Everybody agree? Again, is it the expectation on the AP that you're able to do sine, cosine, tangent of things on the unit circle without a unit circle?
Yes.
Yes. Okay.
We should have like a little unit circle quiz.
What about
That counselor, that's great.
Oh, 100 point that's great.
I think that should be our final. That we just like memorize the circle.
Or we do it like a first semester trig.
I would say.
It's fine. I feel
It's
like
really a hard. Yeah.
You don't remember first semester trig class?
No, it's not always so difficult. That's what we're getting.
Okay. So L'Hopital's rule is clearly what we're going to do here. What's the limit of, or the derivative of tangent? Secant squared. And derivative of x is 1. Derivative of x cubed is 3x squared. Okay. Let's try again direct substituting.
Oh,
What's the derivative, or what's the value of secant at when x is equal to 0? What is secant on the unit circle? 1 over cosine, and cosine is x. So at 0, what is the x coordinate? 1. So I have 1 minus 1 on top, and then 0 on bottom. So that's still indeterminate, right? What do we do? L'Hopital again. Uh-oh. Okay, what's the derivative of secant squared?
oh, we learned this.
Robbie, put that calculator away. It's like, yeah, wait, how does that get?
Oh, okay.
Times what? The derivative of secant, which is
Secant times.
tangent. So this was a chain rule, right? The derivative of the outside is 2 secant x, and the derivative of the inside is the derivative of secant, which is tangent.
Isn't it minus one?
Isn't secant times tangent?
Yes.
Oh.
Yeah, that's a time symbol, is what that is.
Well, I just, I didn't care.
Why is it just tangent?
Yeah.
Party theory.
I mean, that's scary.
Okay. So we have my f of x is x squared, and my g of x is secant x. So the derivative here is f prime of g of x times g prime of x, right? F prime of x is 2x, g prime of x is tangent.
Isn't it tangent secant? Wait, where is that?
Oh, yeah. Sorry, yeah. So this is secant squared. That's what you're telling me. Yeah, okay. Yep.
What?
Yeah.
Yeah.
Yeah. Yep. Yeah.
Times secant is secant squared.
Yep. Sorry. My apologies.
Wait.
It's just no.
My apologies. Yes. I missed what you were trying to tell me. Thank you for not letting it go. Victoria.
Wait, so if it's like, oh, the derivative of tangent is secant squared, but if you can do like the derivative of secant squared, it's just the opposite.
No.
Huh?
No. The derivative of secant squared is not going to just take you back to tangent.
Well, it's gonna be like second secant squared tangent.
No, it's a chain rule.
Right. You just did a chain rule.
Yes.
I just don't understand why it's just tangent. Isn't it tangent secant?
It's 2 times secant squared tangent.
Okay, that's what.
Yes? We're okay?
Yeah, 'cause the
Okay.
the derivative of secant is
Thank you, Mia.
secant tangent. Okay.
I was missing what she was, where we were disconnecting. I think you found it though, right? Thank you. And nobody's called me again. Shame on you guys. Well, this is the, hey, come on now. What do we do? The whole thing is highlighted, right? And I go to drag it, and why is it just taking the one piece?
Because it doesn't want you to write it.
It is like we are fighting today, OneNote.
It's okay, we'll just why my eye? That's how my OneNote is. My OneNote never works. I'm being very bad.
All right.
Okay, if you say that one more time,
So
I'm going to punch you.
let's check. Can we evaluate here if we direct substitute? 2 times 1 times 0 minus 0 divided by 0 is still indeterminate.
Oh, wait, it's the same.
Now we'll get like 0 over 6, right? When we get like 0 over 6 now? See how it goes really down? Right?
Well, hold on 1 second real quick. So we can, or we could do the L'Hopital's rule here again, but we're going to have like this pretty junky looking product rule. Or
Cancel out the 2 and
yes, we certainly could do that. Yes, for sure. For sure, let's do that. I want to point something else out to you guys, though. Remember this rule of limits. Where I can like break up the product. Remember doing that? Why would I want to do that? What's that limit? What? It's just over here on the other piece. Oh, the 3. The 3 is somewhere. Yeah, put it down there. Thank you. Yep. The 3 is somewhere. What's the limit as x approaches 0 of secant squared? 1! So I can just ignore it. Because it's just 1, right? We did that part. And why is that helpful to me? Because when we do L'Hopital's rule again, what did I just avoid having to do? A product and a chain rule together. Right? Right? Isn't that lovely? And here it is, finally. We L'Hopital'd again now. And now we can evaluate this to just be 1/3. Now you could have L'Hopital'd without doing the trick that I did to get rid of the secant squared. The calculus gets kind of sucky. So I was trying to avoid that. But it wouldn't be wrong. You'd end up with the same answer. It still works if you didn't notice that. The limit as x approaches pi from the left of sine x over 1 minus cosine x. First thing I do is I check to make sure I'm in indeterminate form, correct? What do I get? No L'Hopital here. You just do this one from direct substitution. I want to point out to you, if you had done L'Hopital here, what would have happened? Oops. Yes. I did.
Oh. Oh, but it gives you that.
So I want to point out to you that 0 is the correct answer here. If you had done L'Hopital's rule when you shouldn't, what's going to happen? You're going to get the wrong answer. So checking to make sure it is actually indeterminate before starting bombing away into L'Hopital's rule is critically important. You'll get the wrong answer. Well, 1 minus a negative 1 is 2.
No, I knew that. Yeah.
So 0 over 2 is 0 still. Yeah. Hee. All right. What if the indeterminate form I have is like a multiplication problem? How can I do that to make a L'Hopital? Well, if I have f times g, I could write it as f over 1 over g, or I could write it as g over 1 over f, right? That's a little trick to take something that's a multiplication indeterminate and put it into the form of a L'Hopital indeterminate, so we can use a L'Hopital rule on it. So let's take a look at this one. The limit as x approaches 0 from the right of x times the natural log of x. So if this is like f and g, would it be easier to write this as f over 1 over g or g over 1 over f? I'd want g over 1 over f. Yeah. I don't want to put that natural log in a fraction. No, thank you, sir. I'd much rather do that. Huh? Okay, so you said, can you explain that again? And then you trailed off a little bit, and I still didn't. Okay. You're okay? Okay. Right, 1 over x is still just x, right? That's basically what I've done, is I just wrote x as 1 over x, which is still just x. But if I do this now, I'm in L'Hopital land because I am infinity over infinity if I direct substitute this. So this is great for me. I can L'Hopital this. So the derivative of the natural log is 1 over x. What's the derivative of 1 over x? Think about it as x to the negative 1. So how about negative 1 over x squared? And if I simplify that, what am I going to get? I'm going to have 1 over x times the reciprocal. Everybody cool with that? So again, in here, this is all just simplification. There's no calculus going on. I'm just doing algebra stuff to rearrange what I got so that when I do my direct substitution, I don't have something indeterminate. Cool? Ish?
I have a question.
Sure, Paul.
So the 0 to the plus, why does that matter? When you had limit, x is 0 about positive side of 0?
It doesn't super matter to it. It has to do with the natural log piece.
So
Because I can't technically direct substitute 0 into a natural log. Yeah, it tells you that it's going to be like a negative infinity when you do that, but it doesn't really matter to us.
If it's the negative side, I just do the same thing.
Yeah. I mean, well, no, that would be undefined. It's not possible because the natural log, 0 is not in the domain for the natural log, but 0 from the right is.
Right. Okay.
So that's why, it just has to do with the functions that are in there, but it doesn't really mean anything to us.
Are there any tricks like that?
Maybe if there's an absolute value involved, but probably not. All right. So what if we have a subtraction problem where it's indeterminate, like it's infinity minus infinity, such as this one? So let's check to make sure it's actually in this indeterminate form. Secant is, on the unit circle, 1 over x, right? What's the x coordinate at pi over 2? 0. So 1 over 0 is infinity. Great. Tangent is y over x. At pi over 2, the point is 0, 1. So 1 over 0. Also infinity. So this is in the indeterminate form. How am I going to write this as a quotient? That says that's my tip, is try to write this as a quotient. Well, secant is 1 over cosine, correct? Tangent is sine over cosine. So that's two things with a common denominator. Everybody okay there? Now I am in the form that I can L'Hopital that. Oops. Limit. So I'm going to have negative cosine over negative sine. And now if I do this, I get 0 over 1, which is 0. Mackenzie. Not really. Not really. Okay? One, not a quotient rule. No, because I'm doing the derivative of the top and the derivative of the bottom, right? That's how L'Hopitals work. It's not the derivative of the whole thing, which is even better, right? Because it avoids like any kind of crazy quotient rule stuff going on.
Wait, can you scroll up for a second? There's more football. Sorry. I want to see like the text. Yeah.
Sure. All right, we have one more set of indeterminate forms, and that's these that are powers, right? 0 to the 0, 1 to the infinity, or infinity to the 0. So let's see what the trick is to cram one of these into a L'Hopital situation. So each of these cases can be treated as by either taking the natural log. So if I have y equals the f of x to some power g of x, I can do the natural log to rewrite it as a product. And then I can do everything I need there. Or I can write it as an exponential. So let's take a look at an example here. Actually, I think I have two examples cooked up here. Okay. So here, definitely looks like the case where I have like some function to the power of another function, right? This is like f of x to the g of x. So what I'm going to do is I personally like using the natural log rather than the exponential version. They both kind of do the same thing. I just think it's easier to conceptualize the natural log. So I'm going to do the natural log of both sides. And then I'm going to use the power property for logarithms to move the exponent to a coefficient. Everybody's still okay? So what I'm going to do then is I'm going to take the limit as x approaches 0 of the natural log of y, which in this case is the limit as x approaches 0 of cotangent x times the natural log of 1 plus sine 4x. Now, this is still not in a form that I can use L'Hopital's rule on it, right? Because it's not a quotient. What do you think I'm going to do to make it into a quotient? Okay. You could write it as 1 over cotangent in the denominator, or tangent is or cotangent is just 1 over tangent. That's probably what I would do, just because it's a little bit less writing, but it's not wrong to have done what you suggested, Victoria. It means the same thing. Or Elvis, what you had suggested, writing it as sine over cosine. That would be okay as well. I think it gets a little messier because then we have a product property in the numerator when we want to apply L'Hopital's rule there, but it would still be okay. It's a little more work, but everybody's cool? Let's just double check that, make sure this is still in the indeterminate form. Probably worth doing that. If I plug 0 in for sine, 4 times 0 is 0. Sine of 0 is 0. 1 plus 0 is 1. Natural log of 1 is 0. Tangent of 0 is 0 over 1. So we have 0 over 0. This is indeterminate. Should be L'Hopitaling this. I guess I should have checked in the beginning as well. I forgot to do that. Shame on me. Okay, what's the derivative of the natural log of 1 plus sine 4x? So 1 over 1 plus sine 4x times cosine 4x times 4. And then this is over secant squared. Now if I plug 0 in, sine of 0 is 0. Cosine of 0 is 1. And secant of 0 is 1. So what do I have here? And it simplifies down to 4. Oh, but I'm not really done, right? Because what did I just find? I found the natural log of y. So what do I want here? Right? We found the limit of the natural log of y. I want the limit of y So let's say we have the limit as x approaches 0 from the right of y. That's going to equal the limit as x approaches 0 from the right of e to the natural log of y. Everybody's okay with that? Which is going to be e to the limit as x approaches 0 from the right of the natural log of y, which is just e to the 4th. That just x approaches 0 from the right. It's the same thing. It's just a messy looking arrow. No idea.
Like the E's just screwed, like I just gotta backtrack algebra.
E's and natural logs just cancel each other out.
Yeah, no.
All right. I have one final example and we're done Zos.
I thought we were past.
So once you get your answer, can you just do e to the 4?
That's what I'm showing you why the answer is e to the 4.
Oh, I can do that.
Okay. Last example. Quick check that it's indeterminate form. When I do direct substitution, I get 0 to the 0. That's one of our indeterminate forms. So what in God's name am I going to do to this? I'm going to do it the same way. Everybody cool? And I'm going to rewrite this as that. And actually, at this point, does that look familiar? We did that already, didn't we? What? Mr. Kulik. Do you want to redo it, or do you just want to copy in our answer? Copy in our answer. Okay. I'll put a note here. But we're not done, because this is e to the ln of y, which is just going to be then e to the 0. So that's 1.
I followed that.
Okay, so that's it for 4-4. I got some 4-4 problems for you guys to work on. But most of these are pretty quick, right? They're just like, do the derivative for the top and bottom, and then like do a direct substitution. And the derivatives have really been pretty easy derivatives, right?
Yeah.
Like the worst thing we had was like that derivative of secant squared, which is like not that big of a deal. Mr. Kulik just was being stubborn and not hearing what you're saying to me. I'll get these guys up on the class site. So let's talk about due dates for stuff. I don't want to have anything due over break. Just if you're behind, get caught up. If you haven't started the chapter 4 stuff, get caught up. My plan is the day we come back, we're going to start with questions from 4.1 and 4.4, or 4.2 and 4.4 again, and then start banging away at 4.3. I want to finish chapter 4 before the exam. Probably won't have another test before the exam. We'll just have the chapter 4 stuff on as part of the exam stuff. Would be my kind of tentative plan. Is that okay with you guys? No, but the chapter 4 stuff would have a separate test because I think we're going to run out of. I don't want to try to cram another test in and then have like an exam like 3 days later. That seems.
Right, so the 4 is on the exam.
Yes.
With everything else.
Yes.
Oh, my exam's open. No, that's so nice of you.
Probably not, but
Is it still past test questions or no?
what?
Is it still past test questions or is that not? Did you do that? I don't know.
I have typically done that. I probably won't for this because, well, we don't have a chapter 4 test to go from. And then the other 3 tests that I've written for you guys, 2 of them have run way longer than they should have. And if that happens on the final, there's not really much for me to do at that point. So I'll probably rewrite stuff with the effort of, or the hope that things are just going to be a little bit shorter. To take another stab at it, because I know it's what I've done before is just too long. Some of the things are too involved or too difficult or whatever. Okay. But we'll talk about that format here when it gets a little closer. Is everybody happy? Feel fair? If you haven't gotten to the chapter 4 stuff, you have some homework to do over break. If you're still behind on chapter 3 homeworks, you have a lot to do over break. But, don't forget everything in the next week. Reminder, what is happening tomorrow? Finish the test stuff, right? So if you have more to do or something else, stuff you need to look over, make sure you kind of get a chance to do that before tomorrow. Okie doke. Everybody happy? Do you feel like Mr. Kulik's being fair and giving you lots of chances to do stuff?
Yes.
Okay.